So now that we've developed the torsion formula to figure out the internal shear stress due to an internal torque, that's dealing with the first part of Chapter 5. We're trying to, again, go from an internal loading to a shear stress or a normal stress, if it was Chapter 4. That's kind of half of what we do in this mechanics and materials class. We often look at what's the stress acting on some location of the cross-section. That's going to give us an ability to determine whether or not the member is going to fail. So that's only part of what we do. The other part of what we do is we also look at deformation. So in Chapter 4, we looked at the change in length of a column. Here in Chapter 5, we're concerned with a different type of deformation called the angle of twist of a shaft. And again, we talked about this a couple videos ago. If I have a circular cross-section, and again, that's what we're limited to in Chapter 5 to make the analysis a bit easier. Let's say that I paint a point at this location right here in the undeformed state, and then I apply a torque to that cross-section. We're going to find that this point that I painted on is going to move some amount right here. And so it started out relatively horizontal, it rotated up, and so on this cross-section we have some angle of twist phi. But to get to the angle of twist phi, it considers what happened on all the other cross-sections, in or out of the page. In other words, if I were to look at a shaft in isometric view here, this is the same centroid. I paint a point on the outside here at the end, and then it rotates up some amount phi. That rotation is going to, or that angle of twist is going to increase the further that we get away from the support. And so being able to calculate this angle of twist phi, a lot of things are going to be important. Most notably, the length of the shaft. We're going to need to integrate over the entire length of the shaft in order to calculate the overall angle of twist from one point to the other. The way that we derive the equation to calculate the angle of twist phi is based off a previous derivation that we looked at a couple videos ago, when we called that video or that derivation the torsional deformation of a circular shaft. And without going through that entire derivation again, I just want to pull out one piece that we said we would use later on when we're calculating the angle of twist. And the relationship that we figured out during that derivation was that the shear strain at any location on our cross-section is equal to the distance from the cross-section times the differential change in angle of twist from one cross-section to the next. So again, if I were to have two different cross-sections on the shaft, there is going to be, if this is a horizontal line or a longitudinal line, this cross-section number 1 is going to have a bigger or a different angle of twist than cross-section number 2, because that angle of twist is changing from one to the other. All right, so this basically tells us the relationship between the radius, the shear strain, and the change in angle from this first cross-section to the next. That's our starting point for the determination of how to calculate the angle of twist for the entire length of the shaft. And so, again, we're interested in the angle of twist, and so I need to isolate this d phi by itself. So just with some algebra, I'm going to rearrange this equation, and I'm going to say, all right, d phi is equal to, let me get this in the right orientation, gamma times dx divided by rho. All right, so that might not mean a lot in terms of real-world application, but it's just kind of an intermediate step to get us to the point where we can integrate both sides and calculate what the overall angle of twist is going to be from one point on the shaft to the next. So we have a couple intermediate steps to rearrange the right side of this equation to turn it into a form that we can then integrate easily. So a couple important intermediate steps here. We need to apply Hooke's law. Again, here we're talking about just geometry at this point. All right, this is a lot of strain, rotation. There's no actual forces applied here. And the overall goal is that we want to be able to go from the internal torques in a shaft to the angle of twist of the shaft. And so at some point here we need to go from strain to something that's related to forces or moments in this case. And so that's where we apply Hooke's law. Again, Hooke's law is the way that we go from stress and strain or something force-based to something geometry-based or vice versa. So that's how I'm going to get rid of this gamma, the shear strain. I'm going to be able to incorporate something related to shear stress instead. And so an intermediate step here is that we're going to apply Hooke's law. And the way that we're going to replace that gamma is that Hooke's law says that gamma is equal to the shear stress, divided by the modulus of rigidity G, or the shear modulus capital G. Okay, so that's going to allow us to plug in right here. Tau over G is going to go there. All right, but that's only one intermediate step. We need a couple more to get this into a form that we can integrate. All right, so the second intermediate step that we're going to take is that we're going to plug in something else for tau. So when we talked about the torsion formula before, we were able to relate tau to the internal torque, capital T. And so what we said is that tau is equal to the internal torque times the radius, or I'm sorry, times rho, because this is at any intermediate point, divided by J. But in this case, we need to make the formula a little bit more general in the sense that from one side of the shaft to the next, the internal torque might change. We might have a distributed torque along the shaft, or we might have discrete points of application of torque, external torque, and also the cross-section could change, which would change J. Again, J is only dependent on the radius of the shaft, and so we could have a tapering shaft, we could have a shaft that steps down its diameter along its length. And so I'm simply going to turn each of the internal torque and the polar moment of inertia, I'm just going to turn those into functions that are dependent upon the location along the shaft. So we could say that tau is actually a function of x as well too. And again, you have some examples where the torque is not constant, the internal torque is not constant across the length of the shaft, or the polar moment of inertia is not constant because you either have a varying cross-section or it steps down, or you have intermediate external torques applied that would change the internal torque somewhere along the length of the shaft. So I can take this equation right here and I can plug it in to our Hooke's law. And so now I'm going to have phi related to the internal torque, which is kind of our end goal for this derivation. So if I take that, I plug in these intermediate steps right here, I'm going to get that d phi, or the differential change in angle of twist from one section here to the next if these are at some distance dx away. I'm going to get that d phi is equal to the internal torque as a function of x times dx divided by the polar moment of inertia as a function of x divided by the modulus of rigidity, or the shear modulus as well. But again, we usually don't care about just the change in angle of twist between two differential sections. Usually we care about adding up all of those differential changes in the angle of twist along the length of the shaft. And so all that I'm going to do here is I'm just going to integrate both of these sides across the entire length of that shaft. And so what I end up getting is that the angle of twist is equal to the integral over the length of the shaft of tau of x dx divided by the polar moment of inertia as a function of x times the shear modulus g. in the denominator. So like I mentioned in lecture at the very end, this is very similar in format to the other equation that we've used for calculating the deflection of an axial member. And again, I'll put axial members over here, and I will put torsional members on the left-hand side just so that we can compare the similarities between the two. So on the left, we have torsional members. On the right, we have axial members subject to an internal normal force. If you remember, the general format equation for the change in length of a column is the integral over the length of the column of the internal normal force as a function of x dx divided by the cross-sectional area as a function of x times the modulus of rigidity. So the important things, and we'll see this in a couple other chapters as well too, is that when we're looking at the deformation of a member, we're always going to have a loading parameter, some parameter that tells us how effective the cross-section is at resisting that deformation, and then some term that talks about the material properties and how good the material property is at resisting deformation as well too. And always the length is going to be part of that equation as well too. So loading parameter, sectional property, material property, and length. That's kind of the recipe when we're trying to figure out the change in geometry of some member. And we'll see that time and time again. So this is our general angle of twist equation. And just like in chapter 4, we can simplify this down. If we have a member, let's say that we have a member like this, and it's supported on the left side, and it has intermediate torques applied. Let's say this is point A, B, and C. Let's say I have some external torque applied here. I have an external torque applied at point C as well too. And so this does not have a constant internal torque, right? T of x is not constant over the entire length. J of x is not going to be constant across the entire length either because it steps down in diameter. And so we have our algebraic summation that we can use where we simply split this up into individual shafts, calculate what the angle of twist is going to be. It's important to keep track of the signs because some might be rotating in one direction, whereas other parts might be counteracting that in the other direction. And so we say that phi is equal to the sum of TL over JG. And TL over JG applies if the torque is constant and the internal and the polar moment of inertia is constant as well too. And so we have a corollary in chapter 4 with axial members where we sum up NL over AE. And again, remember all of your statics, all of your equations of equilibrium, all of your free body diagrams, between torsional members and axial members, it's almost exactly the same. The only difference is that, let me draw the same member right here, but subject to axial forces. We still have point A, B, and C. But instead of applying torques, all that I'm going to do is apply a normal force. And in terms of shape, the only difference is that instead of calling it capital T, it's a capital N. But all of these are acting parallel to the longitudinal axis and coincident to the longitudinal axis. And instead of a double-headed vector that represents a moment, I just have a single-headed vector that represents a force here. So if I were to go through all the statics to figure out the internal torques between AB and BC, or the internal normal forces between AB and BC, it would be identical. All right, we make a section cut, we sum, in this case it would be we'd sum the moments about that x-axis. Here we'd be summing the forces in the direction of the x-axis. But really everything that you learned in chapter 4 is going to be applicable to chapter 5 as well too.